Swayam Prabha. Digital India. Educated India.
So the number of edges that was blue edges that was incident on P1, okay, the first vertex in this path is going to be is the same number of edges that are incident on this current first vertex in this path, which is that the P0 vertex. So if I add up like this, I will see that the number of reversed edges, the blue edges that were incident on any, if I take all of them in total, the number of reversed edges incident on any of these vertices taken together is the same as the number of reversed edges incident on the vertices in this new path P prime that I have replaced in place of, that I have put in place of P. Okay. So that is basically, this is why this number of the L does not change, that the L, whatever the L value was here remains the same. Now however, can you say what the what the R prime set should be? See, this R prime set, all I have said is the number of reversed arcs does not change, but R prime has actually changed. Can you see why? In this example at least. Okay. Okay, if this is hard to figure out, or can you tell me what R prime should be? I have told you that, well, R prime and R can have R prime cannot exceed the size, the value L. In this particular case, it is exactly, it remains the same size of R and R prime, but R prime can, if you do this operation by, it will not exceed the value L if R was, assuming R was at most L. So now, can you say that if this is how I create, that I will force P0 to be the parent of this P1 in this particular new SBA, and whoever was the original parent of P1 here will now become the parent of P0, okay. Then can I classify what my this number of reversed edges should be in this graph? Note, I said P0 is the parent of P1 in this topological order, meaning in the original graph D. So whoever was the parent of P1 in this SBA can only be a vertex even more stronger than P0, correct? So because of this subtournament, acyclic subtournament property, I know that this edge that I am adding V2 to V5, this cannot be a reversed edge. This edge actually exists in D, right? So here I am not going to spend any, I am not going to have to reverse edges. So where is the reversal of edges actually happening? So, okay. So I can just say that if this is all I did, that I am just going to move P0 to the top of P1 and move down, and PQ at the end gets attached to V5. I know these two operations I can do. Now in the worst case, what can happen is when PQ gets joined, PQ takes the position of P0, right? This might be a red arc and this might be a blue arc. This is a possibility because I have no information as to who the parent of P0 is in this thing and what its relationship is with PQ. So in the worst case, it's possible that this arc actually has to be reversed, right? So I can say that basically take all those edges that are, create the tree like this, and after you have created this tree, so remove, basically see who all are there, the edges that you need, the oriented edges that you need to make this into an SB, like a downward pointing tree, and see, so look at this set, this is basically the reverse set, meaning look at the set of edges that appear in T prime, right, in this thing, and basically look at those that do not appear in AD. That is the reverse set, and by the counting argument we have seen whatever R prime might be, the size cannot exceed R. right? So therefore this is again a valid operation. So I spent a lot of time doing this because I will basically use these two operations to show that there exists a solution. If there exists a solution to a problem, there exists a solution to a problem which utilizes these two properties. Okay. So now we move on to this notion of elite players. Okay. So you understand the notion of types now, obviously. This slide should have come before. Yeah. So this is type 1, this is type 2, this is type 3, this is type 4, 5, 6, and this is, yeah, these are unaffected vertices, so they are type 6. Okay. So here we define a subset of vertices or players is said to be an elite club if this particular property holds true. Every player in this set beats my favorite player. Okay. So here the favorite player is marked as the star. So every of them has to beat this player, this guy. Okay. So interestingly, what happened? Okay. All right. So then followed by the fact that if you take, for example, if this is a type 1 vertex, set of type 1 vertices. Okay. If B is part of the set S, then every vertex that is of the same type as B but appears before B, meaning appears to the left of B, must also be included in the elite club. Okay. So I am looking, so basically what it means is if you pick a vertex of a certain type, every vertex stronger than that, right, who is of the same type must also be in this club. So this is what the second property means. So we will show that, okay, in this example, the elite club would be A, B, C, D. Okay, so C and D are affected vertices. Okay, they are individually of type 2 and type 3. You can always pick them to be part of your elite club. But if I pick B, then A must also be part of the club, or else you cannot call it an elite club. Okay, so basically A, B, C, D, these are the the members of this elite club. Okay. So now we can show, okay, that if there exists an SBA rooted at V star containing L number of blue edges, meaning reverse edges, then there exists an SBA rooted at V star in which all the blue edges are incident on my V star, meaning you just look at V star and all its children, all the blue edges will basically involve V star and L of its children. There are no other blue edges in the rest of the string. That's what this first property means. Furthermore, so I know by this property that V star is one of the endpoints of this blue edges, right? So I should probably change this color. V star is the root of this thing, so of course the edge has to be pointing downwards. The question is, who sits on the other side of the blue edges? It turns out these are only the members of an elite club. So there exists an elite club such that this property, all blue edges go between V star and member of an elite club. Okay. So if I could somehow get my hands on an elite club, then what would happen is that I would know that how to sort of rig them. I would find L of them and just sort of rig them out. So that sort of gives me a way to think forward as to what can happen, right? Okay. Okay, and why do I say that? Basically because if I know which matches to fix, I basically switch the direction of the arc and then pose my original question. Does there exist an SBA rooted at V star, right? Because now it's reduced to the original question that we discussed in the previous talk. Okay. So these are the properties that are used by our algorithm. Now the question is, why do these properties hold? This property can be shown to hold by repeatedly applying that subtree cleanup operation. You keep on sort of applying that operation, and the blue edges basically move one level up, and you keep on doing it until all the blue edges are incident on V star. Okay, and again successively applying that this cyclic shift operation basically allows you to show this property that the blue edges, okay, will only involve members of the elite club. Okay. All right. Okay. So I am going to skip this proof and just assume that this property holds, okay, and show what sort of lies in store. Okay. I'll just assume these two things are true. Now, using those two properties, we can actually show a couple of nice structural properties that basically inform that are used very crucially in the algorithm. Specifically, if the win-lose graph is acyclic, okay. So remember, when the graph was acyclic, our previous question, where does there exist an SBA rooted at V star, that was easy to answer, right? So assuming that answer is no, now I am asking, the graph is acyclic, but you are allowed to switch L arcs, okay. Now, can you answer that question? Like, is there a way to create an SBA rooted at V star? Is it clear what we are saying when we say the win-lose graph is acyclic and posing this question? It turns out that favorite can actually win this, where L arcs have been reversed, if and only if there exists some such set of players. There exists at least this many players that favorite actually beats. And this beat means in the original graph D, like without bribing, okay? This part means without bribery, meaning these arcs are like V star to this arc, non-blue arcs. Okay. So let's, okay, sorry. Okay, so let's just see why this is true. Can you tell why this might be true? Like, can you see why something like this might hold? See, the graph is acyclic, okay? Okay, so let's just do this. So favorite can win with L reversed arcs, right? So it says that there exists an SBA V star where there exists an SBA with V star with blue arcs somewhere in that L blue arcs in somewhere in the SBA, correct? Now, using our previous property, we know that if such an SBA exists, then there also exists an SBA rooted at V star where each of those L blue arcs are incident on V star, correct? So, all these blue arcs are the ones that basically are the reversed arcs, and they are all incident to V star, right? So, now I say that, okay, so if whoever these L arcs are, I know that V star is the root of this tree. So, V star has how many children? Log n children, right? N being the number of vertices in the graph. So, of the log n children, L of these are the ones that have blue arcs incident on them. So, look at these other non-blue neighbors of blue children of V star, okay? These are the ones. So, do you agree if in this subtree, in this graph, if I am sort of write it this way, that these are, say, the L blue children and these are, I want another color, black. No. I haven't gotten hang of this yet. Okay. Okay. These are the non-reversed children. Is it okay? Do you follow? So these are the children on whom the sort of this arcs have been reversed. They are all pointing downwards. These are this thing. Okay. So because of the size property of those of the SBA, do you remember the size property? We said that they always have to be power of 2. There is a child who has size 1, meaning 2 to the power 0. There is a child, the subtree is of size 2 power 1. Then there is a child with subtree of size 2 power 2, and so on and so forth. So we know that if I look at all those children that are blue, sort of the ones that do not have a blue arc incident on them, and sort of sum up their size, okay. So in the worst case, this will be how much? So at least, so see, this is like a very pessimistic count, because I am basically saying, imagine that the smallest subtree, which is like a one child like one vertex subtree, is one of the blue. I don't know where the blue and the black are. They might be always scrambled. I don't know. I am saying that at least the number of the number of vertices that this the total vertices that appear inside the subtrees of the children of V star which do not have a blue arc, they must at least be this much, correct? This is like the smallest possible thing. So then what does this sum up to? Isn't this precisely this value? Right? Do you agree? This is just a simple summation. Now, so basically this says that, so if these are the reversed arcs, okay, so this is, so now can you sort of see why this property can hold? Yeah, I'm sort of proving the forward implication. But the fact that this subtree, this is not subtree, this is a collection of subtrees, right? This is the child and V star is sort of their common parent. These have size at least n by 2 to the power L minus 1, right? These vertices are, remember there are no blue arcs here, correct? So these are all forward moving arcs from left to right. This entire subtree only has, these subtrees only have black arcs, meaning this is the original D arc. Furthermore, each of their root, each of these subtrees that we have, each of their roots are beaten by V star in the original graph, correct? So basically, if I look at the induced subtournament involving the vertices in this set X and V star, I get a directed acyclic tournament, subtournament, where V star is the unique winner, right? So then I know that V star base, so when the moment I have a directed acyclic tournament where V star is the unique winner, basically it means that if I were to have if I restricted the topological ordering only to these vertices, V star would be the source, meaning V star would be beating all these people. So that basically proves the forward direction, right? This is a constructive proof. I exhibited to you precisely who are the people. Not precisely, at least this many people. V star would also possibly beat lots of people here in this subtree, but these are the people. So I need to prove just this, right? So this is the forward direction. So in the reverse direction, if I just knew favorite only beats this many players, can I actually create a subtree? Can I actually create an SBA with at most L reversed arcs, meaning L blue arcs, such that V star is the root? So the forward direction, so this reverse direction is where the thing is. Suppose I have this set, okay, again I am going to call this X, okay, this is the set X. I know favorite beats these people, so if I were to create a if I were to create, okay, so let's see. So I am going to look at this set, this, okay, and partition this set. Can you tell what I do? Partition this set into subsets, of course disjoint subsets, okay, of size. Again, we are again playing with size. Use this formula. This should tell you. trying to find another example where maybe this can be shown. Okay, no, I don't have. Yeah? No. I was just seeing if there's an example here in the paper where, yeah, tell me. It's the same thing. So I basically use this number of vertices. I know this is the size. I will create a set. Okay, I should use U0. Okay, I create a subset x0, x1 all the way to x log n minus n. If x is it is strictly bigger than this, basically remove some vertices arbitrarily, always create an x, split this entire set into this sort of thing. Okay, just the set x, where x0 size, each of their size would be basically 2 power I. This formula, because this sums up to this, tells me that this is possible. X has size at least this, so I can create this thing, correct? However, like using these subset of vertices, create some SBA involving these vertices. Does not matter who the root is, okay? I know no matter who the root is, V star will always beat those people because V beats all of them, right? So basically you create these subtrees like this, each of increasing size, their root, and basically V star is each of their children, okay? And the rest of this set that exists, which is the rest of the set P minus X, or D of like vertices in D minus X, create again the other SBAs from of size, say, whatever the remaining size is, does not matter who the parent is, because they are only, see over here I have created log n minus L SBA. So over here involving these many players, you basically create, I am writing all over the place, L SBAs of appropriate size, right? So whoever this thing is, you basically will make this V star will beat this. Basically, I'm going to force whether or not V star beats this person. In reality, it does not matter. I can always switch this arcs. There are only L of them, correct? And over here, I have the sort of log n minus L of these things, which are from the set X. So I know V star always beats them. So this is, so I have basically created an SBA where V star is the root and only L edges are reversed. Okay? Is it clear? So it's basically just the numbers game. This is why the structure of SBA is so important, because we have all these size values. I know exactly how to split this thing. I know this V star beats, whoever wins, this can be created arbitrarily, and I know that it will cost me no blue edges in this portion of the tree. The blue edges will only be incident on the parents of this. Whoever is the root here in these subtree doesn't matter, because V star can be forced to be, can be made to beat them. Okay. So this is for acyclic graph. Now tell me, where did I use the acyclicity property? You were not paying attention. So in the forward direction, when I was arguing this case, the fact that V star, the fact that you have these edges here, right? These edges, these are all black edges, right? So meaning these are all the original edges. So if V star beats the parent of V star beats the root of this subtree, it means V star, because there are no cycles in this graph, it means V star sits to the left of these vertices, each of these roots. So if this guy beats its child, which it does because it's a black edge, it means V star must also beat this. So because V star beats each of these roots of these subtrees, it means V star beats everybody here. So in this forward direction, I use the fact that it's a DAG very crucially. If I did not have that property, I could not have shown this. Now for when it's not a DAG, then also we can say something. We still have an if and only if condition, but it's slightly a little more relaxed sort of, okay. So what does this mean? That you can have an SBA with L reversed arcs at most L blue arcs if and only if there exists a set of players U, okay, of the same size, notice, but now we are not saying that, we are not requiring that V star beats all of them, but instead what are we saying, that there exists a seeding, because this may not actually hold true, like it's, this is harder to say, this is a lesser of a, this is a more unique condition. We are saying there exists a seeding on this that makes favorite win. So there exists a seeding, meaning there if I only looked at this subset of players and I considered that question, that there exists an SBA, okay, on this subset of vertices with V star as the root, and none of the blue arcs, by the way. This is the original. It's an SBA in the original graph. This is an if and only if condition. And if you think a little bit, you will see that so what happened in that previous case when I was drawing here? Here, instead of explicitly telling you exactly precisely how I am going to sort of doing this partitioning thing, if I only had the guarantee that these vertices X union V star has a subseeding among themselves, which will ensure that V star wins, then this whole thing goes through, right? So that's why that having this property is enough for this one direction. The question is, in the other direction, what do I do? So I say that in this direction it's clear what happened, because this is the part that is given to me for free, that favorite wins, and whatever the other players are, which would be the subtrees, the other subtree, which would be the log, the L remaining subtree. These vertices would account for the log n minus L number of subtrees, right? There are total of log n subtrees. For the other log n subtree, for the other L subtrees, because I am allowed to have L reverse arcs, I can basically use the reverse arcs on the root of that and make V star win. So this condition is true. In this forward direction, can you say what will it be? I say it's even more straightforward, because you have this L reverse arcs, that there are only, and I'm using the fact that all these L reverse R's are obviously just sort of incident on V star and one of its children. So basically what we are saying is there are L children of V star on whom the roots of which are the other endpoint of the blue arcs, right? So if I start with that problem, that SBA, that particular SBA, and then what do I say? The rest of the SBA, that the one that does not have any blue arcs, they have black edges, like they are the unreversed edges, right? And the unreversed edges, so they are the edges that appear in the original graph D. Now I no longer have the acyclicity property. However, what can I say? Okay, so I'll just have to move forward a little bit, because I need to use these things to get to my algorithm. So I'll just leave it to you. If you think a bit about this, it's again a counting argument, so it works. Okay. Okay. So all right. So then, okay. Now see, this thing is obviously this holds. Now if favorite actually beats all these players, it's not that there exists a seeding that V star can win. This property, that there exists a seeding that V star can win, does not require V star to beat everybody. But if V star could actually beat all of those people, then of course it's even a better situation, right? So this is the acyclic situation that is not needed or holds for this non-acyclic case. Okay. So, all right. So now, to get to my algorithm, I am going to define one other form of like maybe I think this is the last definition. Okay, so you are given an SBA, okay, of size n. We define an L removed binomial arborescence, SBA, okay. So I'll draw here. So you have, say, a vertex R, and you have all of its children, V1, V2, and all the way to log n, right? Okay. Now, so this log n, So look, so they have been arranged in the order of the smallest subtree to the largest subtree. So this is a subtree of size 1, okay. This is a subtree of V2 has a subtree of size 2 and so on, and this has a subtree of size n by 2, okay. So that's the thing. Now suppose, so now this L remove arborescence with respect to this SBAT is one where you basically delete these edges. The last L edges, these are L different L arcs, so all representing edges going from root to one its children. So I am saying that delete the last L such arcs. So what you would have is a disconnected graph, right? You have root and it is connected, still connected to its first log n minus L children, and you have bunch of other L subtrees, the roots of which are not connected to the R, okay. So this is what I will define an L removed binomial arborescence. Like the close attention should be paid to the fact that I remove the last L people, the last L subtrees. I remove those edges, not like any L any of the L edges, okay. Interestingly, it turns out that favorite can actually win with L reversed arcs if and only if this win-loss graph actually contains a SBA which is L removed and of course rooted at the favorite. So this is, so what does this mean? This says there exists some SBA, okay, where L of the arcs are reversed. By applying that previous property, I can assume even that the LBA, this SBA that this is, the L reversed arcs are all incident on V star, right? Okay, so this thing tells me that there are some L reversed arcs. I can even assume that L arcs are incident on V star, correct? So V star is the root and you have these L arcs, but it does not tell me which L arcs, right? It could be the first, it could be the 10th, it could be any L arcs could be reversed, right? This tells me no, if there exists such a way that there are only L arcs reversed, well then there also exists a solution in which the last L arcs are incident to the last L arcs are the blue arcs. So do you see, so this, if just because this is true, it's not at all clear why this condition also should be true. So now if this is true, this side is obviously implying that, right? That if the last L arcs are removed, okay, add those L arcs, maybe the worst, always add those arcs as V star pointing downwards to them. Maybe all of them would have to be blue arcs because they don't exist in the graph, but that will give you an SBA with L arcs removed, right? But this direction is the part that is the thing. So suppose this is true, let's assume for now that this is actually true, okay. We'll maybe come back and do the see the sketch of the proof. Now can you define and now can you think of an algorithm? Is this result clear what I am saying? That because of this we actually have, so if you think of how what tree, what SBA you should be looking at, it should be this. V star sitting at the root, its first log n minus L children have no reversed arcs incident on them, okay, because I know that inside they will not have anything, this, and the last L, these are allowed to be blue. So now the question is, what should I do? How do I fill up these information? Like who should go here to these sort of these subtrees and who should go to these subtrees? If there exists a solution, if there exists a solution to my original problem, then there exists a solution which looks like this. That's what this result tells me. So now can you tell me what I might do now? These are also, okay. So let's just look at this is what I am claiming, okay. I'm given a digraph D, okay, and I have this values L and so on. I can decide in this much time to power this to power n and polynomial this much amount of time and polynomial amount of space, okay, if D contains a spanning L removed SBA, T rooted at, this should be B star. If I could do this, then can I answer my question? Then using this fact that this property, if I could, that algorithm tells me tells me the answer to this question. Does D contain a spanning L removed binomial arborescence rooted at B star, right? So because of this if and only if condition, if I can answer this question, I can also answer this question, right? That's the implication here. That if I could answer that the question about L removed binomial arborescence, then I can also, whatever the answer is, yes or no, is the answer to the original question, whether D can actually have an SBA with L blue arcs rooted at B star. Okay. So now the question is, how do we do this? Okay. So I am not going to expect you to know this because it requires a this thing called okay, just to take a step back here and just to tell you more important than how precisely we solve it is is basically what's happening. So look, we were given a graph D, right, the Win-Lowe's graph. We were always looking for a spanning subgraph. And the spanning subgraph had to have this nice property of the SBA properties, right? That's what we were doing all along, the first talk as well as now. Now, in this second part of the talk, the question was slightly modified in that if the original graph does not have an SBA, right, then can I change some L arcs, the direction of it, and then does there exist an SBA, right? So, I can reframe these questions in terms of a subgraph isomorphism problem. You have a host graph, right, a big graph, and you have a pattern graph, and you're asking, does this pattern graph exist in this bigger graph up to relabeling of vertices? So what that means is up to isomorph. So is there a subgraph which is isomorphic to this pattern graph? Okay. Do you agree? Like, is that clear? Do you have any questions? So anyhow, any manner in which you can solve this subgraph isomorphism problem, I tell you, you can basically use it to solve this sort of a tournament manipulation problem. Okay, that's sort of the thing. Okay. So I'm going to tell you there is a way of solving subgraph isomorphism, that it's like a black box we use. Okay. So we have a bigger graph G. Okay. And a subgraph, a pattern graph H, okay. Suppose H, do you know what a tree width is? Okay, never mind. Okay, I'm just going to state it in terms of a, so suppose that the vertices of this graph, okay, are colored, okay. You're using some number of colors, let's call it T colors, to color this, okay, so H is the pattern graph. I'm looking whether H has a, the subgraph isomorphism problem is, does G have an isomorphic copy of H, okay. Now, a further addition to this particular problem is the fact that the vertices in G are colored. So let's call this the coloring function, okay. So this is, say that you are allowed to use T colors, okay, the vertices have been colored. So what you are looking for is not only a subgraph, isomorphic subgraph in G, subgraph in G which is isomorphic copy of H, but also that the subgraph is colorful, meaning every vertex in that graph has a unique color, okay. So that is the question. Now that question can be, so suppose this is of size, so H is of size K, okay, G is size N. Suppose this coloring function is the unique in the sense that every vertex actually gets a unique color, okay. So then automatically if you get a subgraph which is in G, which is isomorphic to H, then automatically it has to be colorful, right, because every vertex actually gets a unique color. So suppose this is the situation. Now for the specific, so in our case this big graph G is the D graph, okay. H is the patterned subgraph. It is the sort of the SBA that we are looking for. Can you tell what should this H be that will allow me to solve this problem? I'm basically trying to solve this problem, right? Okay. All right. So, okay, one other thing that, okay. So, when this, let's just go back to the definition, otherwise, okay, this thing, okay. When I give you a, when I define an L remove binomial arborescence of T, the L remove binomial arborescence you get is unique. Why? Because T is a label tree. From that, you're removing the last L, the edges to its L of its last children, right? So the graph that you get, the new graph that you get, that is L removed, it is isomorphic. It is sort of unique up to isomorphism. I mean, you can relabel vertices, but the structurally it is it's unique, right? So that's sort of an important point here. Okay. Otherwise, that thing I sort of realized I should make that point. Otherwise, it doesn't make sense. Okay. So now, if I know that there exists for a given T, there exists an L unique, there exists a sort of unique T L removed SBA from T, that becomes my pattern graph H. Okay. Now, if my pattern graph H is, now see H here is basically for my, it's a spanning subgraph, meaning all the vertices are present, but some L arcs are missing. Right? And also, so basically what is H? H is no longer a tree because it's a disconnector, it's a forest, like a forest is a collection of trees, right? So now this subgraph isomorphism problem, this colored version of subgraph isomorphism problem for rooted cases where say G is a rooted tree and H is a rooted tree, and you want the roots to match to each other, meaning the isomorphic copies should be such that every sort of the root of H is maps onto the root of G. Then that problem, like that question, is there a isomorphic, does G have an isomorphic copy of H which is colorful, that is every vertex has color, has a unique color, has a distinct color, sorry. That can be answered in Y time, sort of okay, tree. Okay, all right, let me just, this is the time complexity of this thing. This would, okay, this is not H, this should be K. This is, yeah, so this is a K in our K, and T is 1 because tree with, what did I do? Okay, sorry. Okay, so all right. So this is the running time of, I'll just, okay, let's just, this is the running time of the algorithm which gives us colorful subgraph isomorphism which maps root to root. Okay, so this algorithm, when applied to our special case where G, the vertex set of G is the same as the vertex set of H. Okay, this is this, this colorful function is basically a unique coloring. So if I find a subgraph isomorphism, if I find a subgraph isomorphic subgraph in G to H where the roots are mapped to this, so the root of G is mapped to root of H, then basically that solves this question of colorful subgraph isomorphism. So now this graph H is a tree in our case, meaning it's a forest, of course, because there are some of these rooted thing and then there are these subtrees that are disconnected, right? So the set size is n, both of them G and n. This is the tree width, this T is basically the tree width of this host of this pattern graph H. For now, assume tree width is something that you know. For our case H, because it's a forest, tree width is 1. So basically, this for algorithm will yield a time complexity of polynomial in n. So it's basically this, which makes, well, this is basically the same thing as saying 2 to the power n polynomial in n. Okay. So basically this one requires you to know some algorithm which solves subgraph isomorphism. That's what we basically used here. So essentially this is where the whole thing is, this property. Once you know this, and the fact that having an L-removed binomial arborescence uniquely sort of determines the tree that you're looking for, that basically yields this algorithm. So this is the, so it's the L-removed binomial arborescence, that is the pattern graph that for which we are looking for which we are searching for in the bigger graph G. Okay. Okay, so this basically solves, this gives an exact exponential time algorithm. Now remember, we actually started off with saying so anyways, so because we can solve this binomial arborescence, doing a little bit of more work, basically we know how to that the L removed arcs would be adjacent to the vertices which are not currently connected to R. So basically solving this will give you will solve the sort of the original problem, which is that tournament fixing with L arcs reversed. Now we started off with the goal of finding an algorithm with time complexity k log k and polynomial in n, right? So we didn't actually forget that. So now sort of this is probably harder to see, but okay, let's just try and do some sort of some amount of intuition, like let's see why this might be true. Can you say, given that we know how to say find, we have that characterization of this L-removed binomial arborescence, can you use that to give an algorithm to determine whether the given problem, the given instance actually has a SBA rooted at V star with L reversed arcs? Okay, so if you remember what we said, okay, this says k square log k, any problem, so basically this is the result, this is the time complexity you would get if you use one of the earlier algorithms for the TFP problem that we discussed in the previous lecture. So we basically, what we do is, the way, we did not discuss the greedy algorithm, but that can be modified. Instead of solving this problem, that seeding problem where none of the arcs are reversed, we can change, slightly modify that algorithm if you, and instead solve this L-removed binomial arborescence problem. So instead, so actually what is happening is that we are now looking for, we know that the L reversed arcs must be the last L arcs that are adjacent to, that are incident on the root, right? So those arcs are the missing arcs, those are the blue arcs. The rest of the SBA is actually complete. Do you agree? So therefore, by slightly altering that algorithm from the earlier in the morning, we can actually answer, answer this question: does there exist an SBA where only the L arcs rooted at V star and all those things, where only the last L arcs are reverse, like L arcs are missing, no reverse, nothing, we just don't have those arcs. So basically it's almost, this is why L removed binomial arborescence. It's almost a binomial you're almost like solving the original problem that we did in the morning with just some L arcs removed. So you can sort of think that, okay, these arcs exist, whatever the direction you need to give them in order for V star to win, you basically do that. So if you can, once we have that characterization property involving the L removed SBA, we can basically solve all these problems. Because essentially the idea is, we know exactly which L arcs to reverse. They are the last L arcs. Okay. All right, so I think this was all I wanted to say when it came to the technical part. So I'll just conclude by saying that the tournament, this is one version of the tournament fixing problem, which is like the manipulation aspect, like you want somebody to win, how can you force that person to win, and so on and so forth. There are other notions of tournament fixing. For example, if you did not care so much about who was the final winner, but instead you wanted that certain players will play the last round, like the final round. For example, I can tell you in this World Cup, Pakistan is already out of the running. If India and Pakistan played the final, 1 billion people would watch. That is like greater television rating than, like, I don't know, 500 Super Bowls and like NBA, all of them combined. So if a tournament organizer could do that, that would be fantastic for them. So, you can think of a problem like that. I don't care so much of final, but I care about who appears in the last few rounds of the competition. Like, or maybe you want, okay, so this is where the winner is this. So there can be other questions also if you are interested in this. For example, suppose if winning is not an issue, these teams are playing against each other, they have to go to each other's home arenas to play, the distance is very large, okay. So you don't want one team to have to travel a lot, right, going to somebody else's arena and coming back and so on and so forth. Suppose what you have in hand is you are a tournament organizer and you have is the distance of the home locations of all the teams, right, and what you want to do is sort of minimize the maximum distance traveled by any team, and you want to create a seeding, right, the the pathway to the final thing. You don't know who will win which round, but the point is whoever wins, no team will have to travel more than a certain X amount of kilometers. So you can basically change your goal, right, and still ask various types of questions in this tournament setting. Like, you can change your objective. Here the objective was who is winning and why, like, and so on and so forth. How can we find the winner and all. In other cases, you can have other imperatives and sort of that thing. And of course, the basic underlying model can also change. We had a complete directed graph telling us what the various matchups will be. That's the graph that we were working with. You may have a probabilistic graph. The edges are basically probability values. So more than half, like whatever the probability value is, both direction edges exist. They add up to 1 and so on. So then the question would be, what kind of seeding would maximize sort of the probability of my favorite team winning, and so on and so forth, right? Okay. So, and these are all cases when you have the complete binary tree. So there can be other instances in which sort of not everybody has to play every round, your initial rounds are bi and so on and so forth. Okay, so the structural properties are interesting for me personally. I like studying the structural properties because they actually inform the algorithm. Because just a lot of general algorithm, like if you don't understand the structure, you cannot hope to find good algorithms, in this case efficient. If you understand the structure well, there are lots of structural properties one can still think of, and then you can use that to design algorithms. Okay, and the number of upsets was one parameter that we talked about. It seems a reasonable parameter because, as I said, the number of upsets can always be expected to be a lot less than the number of matches played. But of course, you can come up with your other parameters that you want to, that you think would always remain small. This is a particularly important thing when we are dealing with NP-hard problems, when you're looking for, cannot expect to have a polynomial time algorithm, so then you're trying to settle for the next best thing. Okay? All right, so I think I'll stop with that. Thank you.